Hello and welcome to Europractice's webinar series on silicon photonics. I'm Ramzi Salim from Tyndall National Institute, part of Europractice Services, where we work on the full range of silicon photonics from design to fabrication, advanced packaging and system integration. Before we begin today's talk, let me remind you with Zoom and how you can ask questions. So there's a Q&A button at the bottom of your screen. After the keynote talk, we will have a dedicated session for Q&A to answer your questions. So use that button to submit your questions throughout the talk or at the end of the talk. And today you'll hear about CEA-Leti's world-famous silicon nitride photonics platform. Later on, I'll tell you how you can access this through Europractice Services, more precisely through contacting Francois Bartoulet at CMP, a Europractice partner. Today with me is Eleonore Hardy, business developer for silicon photonics solutions at CEA-Leti, where they focus on supporting you from design to device prototyping for integrated circuits and packaging solutions. Hello, Eleonore. Thank you so much for joining us today.
Hello, Ramzi. Thank you very much for organizing this webinar.
It's great to have you with us today. I'm really looking forward to your talk. Do you want to share your screen?
Yes, please. Let me know if it displays on your side.
Mm-hmm. Not yet. There's a little green button at the bottom.
Yes.
And yeah, okay, that's good. So when you click on the green button, it will give you a screen where you can select which one.
I can select my screen.
Okay, yeah, there you go. It's gone through. Perfect.
Okay, perfect. Thank you.
We can see your slides now. Yeah, presentation mode.
Good. Thank you. Thank you very much. So I'm very glad to be part of this webinar today in this great series organized by Europractice. So as mentioned by Ramzi, today we will focus on CEA-Leti's photonics platform and more precisely on its versatile silicon nitride platform. So I am Eleonore Hardy. I work at Leti for now nearly 3 years on this silicon photonics platform as business developer. So I am in charge mainly of the business agreements with our industrial partners, but I'm very glad to also be here today to introduce our MPW services, which you can access through Europractice and CMP. So the overview of today's discussion agenda. First, I would like to introduce you a little bit about CEA-Leti because it's a big organization, and I think it's good to understand where we work here, what organization we are part of. So I will go in a few details about CEA-Leti business activities and the research developments. Then I will go into details regarding our photonics platform. I will first focus on this hybrid platform with both silicon and silicon nitride. And then I will go to how to save photons. So it means ultra low loss waveguides in a few words. And then I will detail what kind of PDK you can get your hands on. And we'll briefly discuss about 3D packaging options. Of course, you have the options offered by Europractice of standard services offered by Tyndall, but we also have activities in this field. So for research purpose, I will detail a little bit. And I would like to finish on let's be creative. So most of you are researchers from research institutes. And I guess you also like to think out of the box. And we will finish with questions and answers. So, about CEA-Leti. So first, where are we located? We are in France. We are located very close to Switzerland and Italy. Grenoble is a big city, even if you have maybe not heard of it before. Very famous for its industry with Soitec, ST, microelectronics just nearby. We have also a big headquarters of HPE and other big industries. It's a city of 450,000 inhabitants with a lot of students. We are lucky, we have a big university in Grenoble, and so it's really an opportunity for us also to get really good students for our research purpose. And so if you take all the high-tech industry in Grenoble and research infrastructures, it means over 25,000 people, so a lot of people working in the high-tech industry here. What you have to know is that Si-Leti is part of a much bigger organization, which is CEA, a research and technology organization, with over 16,000 people working at CEA. We have colleagues working on fundamental research. It's not our case at Si-Leti. We are working on technologies with the aim of developing key enabling technologies for the industry. But when you look at the overall budget of CEA, it's over 4.4 billion euros and almost 6,000 patents in its portfolio. So it's a big research organization. Inside CEA, you have CEA Tech, which has a very specific mission of bringing those wonderful key enabling technologies to the industry. So we are not an industry ourselves, but we really want to be the bridge between research, development, and industry. So we have teams in CEA Tech really specialized in transferring technologies to the industry. So part of CEA Tech, you have Leti, the organization I'm part of, really focusing on micro and nano technologies and integration systems. You have Liten working on advanced materials, still to be integrated in micro and nano technologies. You have List working on software development, because when you think about those high-tech systems, at some point you also need to have a smart software behind to run it. And you have also some offices spread in France to really be close to our partners, French partners. So CEA Tech is more than 4,500 people, about 650 million euros budget, and we are over 4,000 patents. So Leti, the organization, the institute I'm part of, inside Leti, we have several platforms, not only silicon photonics. So of course, today's discussion will be really focused on silicon photonics and our platform has been recently transferred from 200 millimeter wafers, 8-inch wafers to 12-inch wafers, 300 millimeter wafers. So we will focus on this in this talk. But I wanted also to let you have a view of all the platforms we have here in Leti, in Grenoble. So we work also on CMOS FD-SOI, on technologies beyond CMOS, power GaN, MEMS, embedded memories, imager, LED for all display applications, 3D integration, and we also have an activity specifically on SOI substrates. And so in this field, we have a joint lab with Soitec, which is an old spin-off of CEA-Leti. So you see we have a wide range of technologies in hands here. So let's focus a little bit on optics and photonics. So in Grenoble, in Leti, we are over 1,900 people. And each year we create new startups. So this is really in our mission, whether to transfer the technologies to the industry, if we find an industry that is relevant to welcome this new technology. But if we don't find it, we have the opportunity also to create our own startup. So this is one option. So the Optics and Photonics division is now quite old. It's more than 40 years old. It's about 300 people working together, mainly researchers, engineers, and PhD. And we have 90% of our revenue that is coming from outside CEA. So this means it's really important for us to find partners in Europe or worldwide to work on development programs. So we are part of numerous European projects, and we also have bilateral agreements with industrial companies. Most of them are confidential, so we cannot discuss much of it, but so it's a good balance we have. And of course, one of our mission is also to innovate, and that's why we do care about new patents. So we have about 500 patents in our optics and photonics patent portfolio, but we renew those patents every year. We decide which one we leave and which one is important to keep. So we have about 80 new patents each year. So in the Optics and Photonics division, of course, we have a part of our team focusing on integrated optics, photonics integrated circuits, on silicon nitride platform. And in this frame, we have long-term partnership with Si-SiN Lab. So Si-SiN Lab is a consortium with Thales and Nokia and CEA. And also we have development activities with ST Microelectronics. But all around those activities, we have other activities I already mentioned through the description of our numerous platforms. So we have activities in display with micro LED, Alidia, Soitec. We have also activities in infrared imaging, so with LINRED and the European Space Agency. We have also activity in X and gamma imaging systems, thermal and terahertz imaging, materials, and this is very important for us to have this know-how on how to innovate on materials, because it's always a challenge we face to integrate new materials in our platform, in our photonics platform, so we can rely on our colleagues working on new type of materials. We work also on optical sensors, and maybe this is a difference from other research and technology organization, but optical sensors is separated from the PIC activity. So we have another team really focused on optical sensors. I will not talk about it today because I'm really into PIC more for telecom datacom applications, but of course our platform is also used for biophotonics applications. And so we have other activities in CMOS image sensors, semiconductor process, new process for our fab. And we have solid state lighting activities to develop new type of LEDs and 3D imaging systems. So we can mention LiDAR as a really famous application. And it's true that we also work on LiDAR system based on silicon photonics platform. So it's very much linked to our topic today. And we have activities on packaging. Now let's go directly into what brings you here. What is our silicon photonics platform at Leti? So we have a silicon nitride photonics platform. So we have both a layer with silicon in which you can find so different types of gratings, strip waveguides, shallow rib waveguides, deep rib waveguides. So you see we have 3 etching levels. It's very important in order to optimize depending on the functions of your waveguide. So for example, if you want a grating coupler, you don't want the same etching depths as if you want a modulator, for example. You see we have so also the actives that are part of this silicon layer. So we have modulators and photodiodes. So we have germanium epitaxy for the photodiodes. We have implants. So we have 6 implant levels for the modulators. And then we have silicidation on top for the contacts. And if you go from the bottom to the top, you see then we have the silicon nitride layer. So this is a new layer we have introduced a few years ago. First, it was on our 200 millimeter silicon photonics platform. And for a year now, we transferred everything to our 300 millimeter platform. So this is now the typical cross-section of our 300 millimeter platform. So you see the silicon nitride has 2 etch depths. And the silicon nitride can also be used for edge coupling, butt coupling. So it really depends. Some people are really good with grating couplers, and in this case, you can also use silicon nitride with the silicon to have a silicon-silicon nitride grating coupler with great performances, and I will talk a little bit about that. But if you prefer to have edge couplers, this is also possible, of course. Then you might also need in your circuit some phase shifters. So we have a heater level, metallic heater level. And on top of that, we have 2 metal levels for the back end of line with vias. So here you see the typical cross-section. You can find it on the CMP website, and you can find details about it on TMP website. So all the things I will explain today, you should be able to find it in the brochure of CMP. Now the question is, why should I use silicon nitride on top of my silicon? What is the advantage of bringing in those 2 layers? Here you see a typical example of a photonics transceiver. So here you see that you will need, of course, actives to modulate your signal, to transmit the exact information you need. But on the other parts, it's only passives. You don't need actives, and in this case, it can be very a good advantage to use silicon nitride to reduce the loss of your circuit. So first advantage is usually to use silicon for actives and keep silicon nitride for all the passives. So in this case, you will get low propagation loss in the silicon nitride part with 0.6 dB per centimeter propagation loss. But a second advantage is also the good thermal stability of silicon nitride. And it's always a challenge to manage the thermal behavior of a system. So it can be a good advantage to introduce silicon nitride for this purpose. And as we will see just after, it's also good to combine silicon and silicon nitride for some components for a better broadband, wider broadband coupling into your circuits. Here you see the transitions between silicon and silicon nitride are below 0.1 dB. So it's not much. So it's quite easy to combine a part with silicon and a part with silicon nitride in your circuit. And here you see a typical cross-section of a silicon waveguide with its silicon nitride waveguide on top, just located where you have the transition between those two. So typically we work with a 600 nanometer silicon nitride and with 300 nanometer 8 silicon. This is what we offer in our standard platform. Of course, we are a research organization, so we like also to play on those thicknesses for some specific developments. So if you are also looking for other layers for specific projects, so out of MPW offer, please do not hesitate to contact us. So what can you do with a silicon nitride taper? You can do a very good coupling element. So here you see an illustration of edge coupler with silicon nitride. You see the 200 nanometer silicon nitride tip, and on the, or I don't see, let me use my pointer. Yes. So you see this is the silicon nitride tip, and in front of it you see the fiber, the lens fiber. So the mode field diameter can be 2.5 micrometer, and the coupling insertion loss is below 2.4 dB in the O bands. So this is a very convenient component, especially for CWDM modules. But what else can you do for as a coupling element? You can also use silicon and silicon nitride for an hybrid grating coupler. So in this case, you have both layers with different gratings at the silicon level and silicon nitride level. Why we do this? Simply because if you use only a silicon grating coupler, so this is a black curve you see here, you will have a good insertion loss, I mean very small insertion loss, but it's not really broadband. And it's a problem when you have a CWDM circuit, for example. And on the other hand, if you use only silicon nitride, so this is a blue curve here. Yes, it is broadband. You can say you can get 50 nanometer broadband bandwidth at -1 dB, or even higher if you go down a little further. But the insertion loss are high, and so you lose too much power to use only a silicon nitride grating coupler. And if you combine silicon and silicon nitride, you get the green curve here, meaning that it's a very good compromise between getting wide bandwidth and a low level of insertion loss. So you see a picture here of these two levels grating coupler. What else can you do with silicon nitride? So we have seen a scheme of a transmitter circuit just before. For the MUX or for the DMUX part, it's the same. It's very convenient to use silicon nitride because you will get very low sensitivity to thermal changes of your system. So here you see an example of manufacture MUX with silicon nitride. You see the transmission of the 4 channels, CWDM. It was done with our 193 nanometer deep UV photolithography, and we got below 2.5 dB insertion loss with a crosstalk below -30 dB and a bandwidth -1 dB around 8 nanometer. And what is really, once again, very convenient here is that you get very little thermal sensitivity. Basically, with silicon, you would get 6 or 7 times more shift in wavelengths than using the same mux demux in silicon nitride. So it's a big gain. So each time, on each slide, I put some references of the last papers on the subject. So you are free to find more details in these papers. Now let's go to saving photons. So it's not saving Ryan today, it's saving photons. We know it's really important for many applications to find a way to keep our photons till the end. Of course, we can think about quantum applications. It's the most obvious. It's critical not to lose your photons on the way. But even for Datacom application, it's a big challenge to reduce the losses. And for high complexity circuits, like in neuromorphic photonic, with very large circuits and a high number of components, it becomes also very critical not to lose too many photons on the way. So we have worked on a specific step that we introduced in our standard flow. So it's a nitrogen annealing process that we have now introduced as a standard process in all our flow, photonics flow, in order to reduce the sidewall roughness of waveguides, all type of waveguides, rib, strip, or deep rib waveguides. And it's amazing how good the results are, and we are very happy with those developments because now our new standard of propagation loss in silicon waveguides are much smaller. So we reach now 1 dB per centimeter for strip silicon waveguide in the O band. We reach 0.1 dB per centimeter for rib silicon waveguide in the C band. And here you can see how great those improvements are. So you see in blue the propagation loss before, without any annealing process, and in green after we introduce this annealing process. So it's a big reduction. And now it's really standard. Of course, we had a few questions while developing this process, like will this affect the other passive components? Will this affect the performances of all of our components, active components as well? And so we have run a lot of short loops to make sure we had no alteration of the performances of the other components, and the performances stay exactly the same for all the other components, or even they can get a little better. I will explain. I will give you an example. So here you see also the good homogeneity, the good wafer uniformity we get with this process. So it's really a key process now we use in all our flows. And on top of that, as we moved from 200 millimeter process flow to 300 millimeter process flow, we also take advantage of a brand new immersion lithography tool, which means even better uniformity at the wafer level and better patterning for all our waveguides. So this is not published yet, but it is on the way to be published. So you should be able to find the publication related to those results very soon. So I mentioned that you can also get better performances for other components than waveguides. So we looked at Maxender modulators, PN junction, and we, in this case, use deep rib waveguides for the junction. And we have observed with for example, 1 millimeter long and Maxender modulator, that we have 1.5 dB gain for those modulators. So we reduce the losses also for Maxender modulators. And the efficiency of those modulators is preserved. We are still around 1.6 volts centimeter if we look at the VPLP of those Maxender modulators. So it means that it brings only better performances at all levels on the platform. Now we have had a look at this platform, and some people like to dive into more details on how this is processed. So I would like to show you, oops, sorry, it seems like the video is not appearing. Okay, let me try a trick. Good. So I will not go over the advantages, many advantages of silicon photonics that you are all aware of. I would like to really dive into a SOI wafer with you to look at this cross-section I just presented you. So first, we have the implantations. 6-level implants. Then we have a 3-level of patterning for the waveguides, for the modulators as well. Then we have the encapsulation, silicon oxide encapsulation. We have an opening for the germanium epitaxy. We then add the silicon nitride layer. We pattern this layer with 2H level. We add the metallic ether level, and then we finish with the standard 2 metal back end of line. This means at the end that we get for, let's look at emitter. It's really representative of what you can do with photonics platform. You get a grating coupler, 1D grating coupler with below 2.5 dB insertion loss. Then you get different directional couplers. You get some MZI modulator with loss below 1 dB per millimeter, and efficiency can go below 1.5 volts centimeter. And you have low loss waveguides, no matter you prefer rib, strip, or deep rib. And you have low loss transitions as well. If we look at an arrayed waveguide, a MUX or a DMUX, you get low insertion loss, you get a crosstalk over 20 dB. So those are the typical components that are part of our component library that you will find in our PDK. So you get everything ready to just design your circuits based on those components. You also have the possibility to use 2D grating couplers, still with low, relatively low insertion loss. You have then the possibility to use the silicon nitride layer. Of course, if in your circuit you think you have no use of the silicon nitride layer, you can just use the silicon layer. It's also a possibility. But you know that this layer is also offered. And then you have photodiodes. So germanium lateral photodiodes with responsivity over 0.8 amp per watt. So here it is. This is a view of our photonics platform, silicon nitride platform. It's, of course, a very versatile platform, as you have seen, for communication application, for sensing application, but also for HPC, quantum, neuromorphic computing applications. Good. So we have had a look at several components that you can find in our device library. So we have a device library for the O band, for the C band. We have fixed cells, parameterized cells, and some black boxes for sensitive components. So you will find in a CMP brochure a list of some of those components with typical specifications in the O band and the C band. If you don't find the components you need in this list, just let us know. We have more devices in our hands, and so on case by case, we can also bring you additional components for the aim of your specific circuit. About the PDK, so until very recently, we were using a PDK for our 200 millimeter platform. But as you have now understood, we have migrated to 300 millimeter platform. So currently, the PDK we offer mainly with Cadence and Montor. So it means that for the front end, for the layout, you can use Cadence Virtuoso. For simulation, you can use Eldo from Montor. For verification, you can use Calibre. And for finishing, for yield enhancement, you can use a Smart Fill from Montor. So this is the current PDK available. We also work in close collaboration with Lucida, and from time to time, for some specific users, Lucida is also offering services to offer a IPKIS version of the PDK. And we used to work also very much with Synopsys, and so in the future it will probably be possible to also get your hands on a Synopsys PDK, but today this is what you can get. 3D packaging, just a few words. So this platform, as you will see on CMP website, is compatible with Open3D Post processes. So meaning you can have several options offered through Open3D Post processes like UBM, micro pillars, copper pillars, for then integrating your EIC with your PIC. So a TIA for a photodiode or a driver for a laser. So this is totally compatible with this offering. And now I would like to say a few words about what we can do apart from those very standard services offered at CEA-Leti for our silicon nitride platform. Because you are researchers, and we are researchers too, we like to think outside the box. And so we don't like to stay really in this box and not change anything. So we have plans to add new layers. We have plans to add a few additional services. So for many years, we have worked on the packaging part with wire bonding at first. Then we moved to flip chip technologies with several partners. Now we work also on TSV as an option. So I would like to say a few words about that. This is something that we are currently developing as part of two projects. One is a European project, a MASTART project. And so I would like to say a few words on that. And also, I would like also to say a few words on other needs you may have for 3D packaging, multiple fiber pigtailing, RF module implementation, wire bonding, chip-to-package assembly. So we have teams working on that. If you need it for MPW project, you know you can rely on services you're offered by EuroPractice. But if you are thinking also of specific needs for dedicated projects, please be aware that we have such services as well. So about TSV, I would like to stop just 1 minute on this topic. There is a big trend in developing a silicon photonics interposer, and of course we are also in this realm of developments. So we have developed solution with TSV last and TSV mid. So I wanted to just show you a few illustrations of what has been made in this field. So for TSV last, so you see here an illustration with 200 micrometer TSV with a 2 micrometer copper liner. And for the TSV mid, you see also another illustration that you can find in a recent publication made at ESTC this year, showing the results. So I will not say much because this is not part of the MPW service today, but if you have a dedicated project in which you think TSV makes sense, we would be really happy to discuss this with you. I wanted also to stop 1 minute on 3-5 because 3-5 is a big topic at CEA-Leti for many years, and especially integration of 3-5 on silicon, so on SOI. And so just for you to know, this is something we have worked for many, many years. It's an approach very similar to what Intel does for its transceivers. So we have this approach of collective 3-5 die to wafer bonding, and then we pattern at the wafer level the 3-5 material with CMOS compatible process. So we have first developed this with a front side integration of 3-5, and then we have moved to a 3-5 backside integration. So you see here 2 different cross sections. And you see in the latest one that we also have this possibility to integrate 3-5 on a silicon nitride photonics platform with a backside integration of 3-5. I will not go into details on why it's so important to have 3-5 in your circuit. You know that a big challenge is to get your laser, your SOA integrated in your system. If it's a switch, you may need SOA, a high number of SOA in your circuits. And here, so having this collective die to wafer bonding, it means that you can really select what kind of 3-5 you need. What, for example, here it's with indium phosphide, but it can be with InGaAs or other 3-5. So you can select the exact AP you need. You can have very small dies of your 3-5 material. With very close dies from close to each other, and this is a process we are using in 200 millimeter, and that is also scalable in 300 millimeter wafers. So just an illustration of what we do also outside the standard MPW services. One other thing I wanted to point out is that we also work on a stoichiometric silicon nitride LPCD, so with LPCD deposition, for ultra low loss waveguides. So in this case, so we have developed this specific deposition to get 0.03 dB per centimeter propagation loss. So it's another level of low propagation loss in waveguides. It's mainly used for quantum technologies development. So we have, for example, illustrated this with silicon nitride micro-resonators. But once again, it's just for you to know that outside the box, there are other things we can bring you regarding photonics. So last slide, the takeaway. So there are many challenges today in silicon photonics. If we look at communication applications, of course, everybody is looking at increasing the data rate over a terabit per second of data. And in this frame, adding silicon nitride in the platform is a very good advantage because you get broadband components and you get athermal devices for MUX, for example. Another challenge of silicon photonics is the high complexity of novel circuits. For LIDAR applications, for neuromorphic applications, circuits are becoming bigger and bigger. And with this increased number of components, once again, you need to save photons. So having this low loss photonics platform is, we think, very, very important. And another challenge is also the density. That is also another aspect of the complexity of new circuits. You also have higher density level of your components. And so we have the advantage of this new 300 millimeter photonics platform with immersion lithography. So the typical smallest feature size of our MPW is about 100 nanometer. But we also have the possibility to go down to much smaller feature size with immersion lithography. And so it means new possibilities in terms of design. So of course, you are welcome to use our library of components, but you are also welcome to use our design rule manual to design your own components, maybe slot waveguides or other components. So the last word is we are aware of all these challenges in silicon photonics. We are researchers like you, and we are pushing our photonics platform to the best it can get to really answer all those needs. So Ramsey, it was my last slide.
Thank you very much, Eleonore. That was excellent. Very, very interesting. Well, folks, I'm sure you have lots of questions. And before we open up the floor to Q&A questions, remember there's the Q&A button at the bottom there. I'll just share my screen here to show you how you can access some of these technologies. So that Eleanor's been mentioning. So yeah, so if you go to our website, you can find there the full CEA-Leti technologies offered through CNP, who are part of Europractice, and they will be giving you support for design, fabrication, and packaging of components and systems. And in fact, you can see here also on the website, you'll be able to find the CEA-Leti MPW schedule run. Here you can see that the schedule run for 2020, the next run is in 3 days. So I imagine if you haven't already submitted for that, that might be a bit tight for you. But fear not, 2021, there's runs scheduled for then as well. So in Q2, there'll be some runs coming in, as well as Q4. But if you keep updated, just keep an eye on our website for the latest announcements. So in Q2 of 2021, there'll be the next runs. In the schedule as well, you'll notice that there are these dates or deadlines. These are the GDS final submission deadlines. So you want to have registered at least 2 weeks in advance with CMP, so that they know to look for your design and to kind of give you that right support for it to be submitted. And if you have any questions or you want more information about it, the best way to do that is to contact Francois Berthollet. So that's francois.berthollet@mycmp.fr. So yeah, I kind of will open it up to the Q&A